Hello and welcome to my class. I'm Grolin Annalisi from ThinkMO Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 5834444290. Today's topic is dynamic routing, EIGRP theory and experiments. Before the official start of class, let me start with the unfinished part of the last lesson about static routing. Tell everyone. Then talk about the dynamic routing part and the first dynamic routing protocol. It is also a routing protocol proprietary to Cisco, EIGRP. Do you guys remember this topology? We've covered this in the last class. And the interconnection of 3 devices is also finished. Here we have not configured. This corresponds to the last part of the static route. That is load sharing. Let's first look at this picture. There are now 2 devices. There is a network segment behind the RB. 8.8.8.8. Everyone can see. Here in RA there are 2 lines. Can reach this network segment. Look in the routing table. Has 2 next hops. One is the address of this interface. One is the address of the interface below RB. That is, we have 2 next hop addresses. Go up and go down. Can reach the same destination network segment. We talked about the principle of adding tables to routing. If it is the same routing protocol, we will compare the value of cost. But static routing is different. If the management distance is the same. Same goes for routing metrics. Then both routes will be placed in the routing table. This is what it looks like in the picture now. Load sharing. When data is forwarded, 2 routes can take effect at the same time. Let's finish this experiment now. Because there are some leftovers from the last class that I didn't do. Let's turn the device on first. During the opening, let's look at this picture. I added 2 switches in the picture. When everyone is doing experiments after class, also try. Let you touch the device first. That is, when you add nodes, just add a second layer here. When selecting an icon here, choose this. It doesn't need any configuration. Just put it here. I have entered the planned network segment on the map. Let's take a look at the situation today. It starts up a little bit slowly. Let's review first. If I want to configure it, we first under these 2 interfaces, configure the address. Then on the router on the right, configure a loopback port address. 8.8.8.8. A host route with a 32-bit mask. OK. Now in. We start configuring. Open them first. On the left is R7. I give it a name. It is slightly slower. If the device is turned on after, everyone must remember. You need to name the device first. Because for many simulators, inside is the same. When you have too many devices, its name will be cumbersome. So I just type them in as R1 and R2. OK. After we rename these 2 devices, we'll enter the interface. It is configured with an address. I put a screenshot of this image above. Let's do an experiment. In this process, just look at my configuration. This is basically the same as the previous static routing. So there is no need for everyone to practice after class. Enter the 00 interface. The address we assign to it is 10.1.1.1. Then enter the 01 interface. That is the following network segment. 20.1.1.1. Then the R2 device. .1.1.2. Finally here. Give it up the address of a loopback port. The address of the loopback port is 8.8.8.8. Here to remind everyone. If you up a loopback port, you do not need to manually shut down this interface. It is enabled by default. We can check. Show IP interface brief. Let's check the status of the interface. You can see. The loopback interface is now enabled by default. It does not need manual shutdown. A classmate once asked me a question. When typing the command, what does this BR mean? You can view some brief information about the interface. For example, if you only check the IP interface here, it will be more informative. So if you want to just see a summary, or say you want to just look at some output, you want to add this BR to the current list, called brief. Here are some configurations for the base of the two devices. After the interface is configured, we're going to test the direct connection first. This is the eternal truth. Test 10.1.1.2. That is, test the peers to see if they can communicate. Same. I will test 20.1.1.2 again. Make sure that the directly connected interfaces on the two links are not misconfigured. I hope now. From the router on the left to 8.8.8.8. So how many routes do I need to enter here? If I want to implement a load sharing, how many routes do I need to enter? Okay. I need to enter 2. We first need to enter configuration mode. Remember how to configure static routing? IP route 8.8.8.8. We go to a loopback address like this. This is an exact host route. The next hop is 10.1.1.2. Then go up now. Similarly, I will enter another next hop. 20.1.1.2. I configure them. After configuration, we can view it on the device. Show IP route. Look at the routing table. This achieves the same effect as before. For static routing, if now going to the same destination, the next hop is now specified. And do not specify other parameters. It is load sharing by default. We can test it now. For example, I am here to ping 8.8.8.8. Okay. It is able to communicate. Then we use tracer out. Give it a track. Let me tell you first. If you want tracer out to be faster, you need to turn off the function of domain name resolution here. You can remember this command. No IP domain. We enter configuration mode. You must turn off the function of domain name resolution. Otherwise it will be slightly slower. After closing, we start traceroute. I now wish to trace 8.8.8.8. Then go to check. Which nodes will it pass through? I'm now back to my daily order. For example, I'm going to traceroute it now. If using traceroute, what parameters is it based on? To complete such a function? That is, which parameter does it use? For example, it uses an ICMP message. But which parameter it ends up passing? To achieve this one-by-one tracking effect of nodes, based on the TTL value of the 3 layers. When I send a message equal to 1. Go back. Send a message equal to 2. Go back. Can track the nodes that can be reached now. This is what we call traceroute. Let's trace 8.8.8.8 now. Let's check. For now, if you enter the traceroute command, actually there are 2 ways to go. It will all finish showing. I just make it show a. For example, I enter a 1 here. This means that when I traceroute, returns only 1. Traceroute has 2 functions. In addition to being able to track all the equipment along the way. In fact, it can also do a multipath detection. For example, there are multiple paths to the destination. It is possible to conduct a detection. But we are here. Enter a value to have it return only 1. Let's say when I first type, it returns 20. The second time is 10. Every time I'm doing the next probe. That is, I want to see which addresses I can go to when I arrive at my destination. It actually recurs. The appearance of a loop means that the packet is now going like this. A message goes up. A message goes down. It is when the message is detected. Packets are also loaded. Go up first. Go down. Means that the 2 paths are equivalent. It's different every time. Actually, this realizes the load sharing of data. But in addition to load sharing is not enough. Often multiple links in addition to such sharing. There is another need. Route backup. Also known as floating routing. There is a scene on PPT. But let me tell you another scene. That is, in the current enterprise network, a more common form. This picture shows 2 devices. It's still the same experimental scene as before. Then I hope. Make the above line the main line. Let the following line be used as a backup line. I'll draw a picture for you to illustrate. This is in our actual work now. When will we use such a technology? Let's talk about an environment where companies export. For example, now the following device. As a gateway for the company's exports. The company's export equipment must handle the business of the operator. For example, if you want to browse Google or WeChat, the connection here is the operator's network. Often for companies. When we handle broadband business, we'll not handle only 1 line. Because it's called a single line. A single line is prone to a single point of failure. If there is a problem with the interface between the operator and me in the future, or there is a problem with the interface of this export device, or there is a problem with the line I handled. In short, it may cause problems with the current line handled by the company. For the current internet communication as a whole, this situation is very dire. For example, there is a switch below. Switches may be connected to other switches. There will be a lot of end users waiting to go online. Our daily overall business traffic all go through the company's gateway exit. We all rely on it for access on the internet. Then all traffic. In the end, if they all converge on this 1 line, then think about it. If there is a problem with this line in the future, then the whole business stops. We're going to draw another line here. We often handle business with multiple operators. But I got 2 broadband. Definitely not all high bandwidth. Because it's too expensive. So often we will choose to do 2 different. For example, the one on the left is 500 m. The one on the right is 200 m. The main daily business is on the left. When all employees communicate on a daily basis, traffic goes to the left. Then if one day this line is broken, we'll take the alternate route. The spare line bandwidth can be smaller. Because it's a backup. The backup will only be used if there is a problem with the main line. Then I don't need to spend such a high price to keep it. Just a little cheaper. Although the bandwidth is small. But when we cut to the backup line, can give some time. Repair and salvage of main lines. This is its actual application scenario. Certainly. When the main line is restored and can be used, we will also choose this route for forwarding. This picture is a little bit simpler. No scene drawn. Only one configuration is drawn. But the meaning is the same. Put it in this picture. What does it mean? For example, I made this line into a main line. This line becomes a backup line. Now two routes added to my routing table. But adding it to the routing table means when data is forwarded in the future, two routes are equivalent. The traffic above and below is loaded. Assuming that the above bandwidth is relatively large. 500 M. Suppose the following bandwidth is 200 megabits. The daily traffic will follow the above route. If something goes wrong with this line, go down this line. That is, I only want this route to be added to the table. When we looked at the routing table just now, in this position, it is a fully consistent route. Remember what those two numbers represent? We talked about when the administrative distance and routing metric are consistent, multiple routes will be added to the table. Equivalent routing. On behalf of them when forwarding data. Their abilities are the same. I now hope that the above route will lead down first. Because I want daily traffic to go above. Then how do I? Can it control the routing? For example, I wish now. Daily traffic only takes the above route. Do not follow the route below. We can choose to add the above line to the table. And the following lines are not added to the table. So how to control it without adding a table? You must remember a word. The best path is always stored in the routing table. Only when the path is not comparable. Like this situation. Administrative distance and routing metric are exactly the same. We will add. Now if I want to artificially control an appearance, remove it from the routing table. What method should I choose? Think about it. Only if they are exactly the same. Both routes will be added to the table. I now hope that there is only one route plus table. I can change these two parameters. Let another route not add table. But for static routing, administrative distance is 1. This is generally not modified. We only modify the routing metric. That is, we can adjust the routing metrics by. Then let another route lead down from the routing table. Forwarding only on the main line. Here is a sentence. Floating routes in the case of failure of the main route in the network will be added to the routing table and undertake data forwarding business. That means every day there is a route that does not add a table. This route is called a route backup. It has a name. Floating route. When routing table, we can control it. Control routing addition table. For example, the default administrative distance for static routes is 1. If we modify, I want the above route appear in the routing table. The following route does not appear in the routing table. Then if I modify the administrative distance, how much should I change it to? You have to remember. Smaller is better. So if you want to have multiple static routes, let a certain link or a certain route. Choose it first. Then we can choose. Increase the administrative distance of other routes. We can accomplish such a situation. So let's do it. I am now viewing the configuration just now on R1. I teach you a command called show running config. I'll check it out. Now included in the configuration just made. What are the configurations about routing? IP route. Okay. Here are two routes. So since we want this preference, we just hope this one goes down. So, I want to be in configuration mode. Cancel this route for it. No. And copy it over. Now this configuration has been cancelled. After cancelling, we reconfigure. That is, reconfigure the route just now. But after the configuration is complete, we can put a question mark in the back. Enter a distance metric in this. Is the administrative distance of this route. We can be here. Modify the administrative distance of this route. 1 is a default value. I want it to be greater than 1. Because it is greater than 1 it is not good. The smaller the management distance, the better. So I'm assuming to change it to 2. What is written in the PPT is 100. But it doesn't matter. Greater than 1 on the line. I changed it to 2. Let's still check the configuration just now. Now, when I'm doing routing check, we'll find there is no number behind the first line I configured. Because it defaults to 1. Default is not displayed. The management distance in the second one is changed to 2. Everyone can guess. Now for the two configurations. Its administrative distance is different. Then according to the principle of adding table we thought before, when all destination networks are the same, we'll trigger the comparison. Now they are both 8.8.8.8. 32-bit mask are the same. The destination network and mask are the same. We'll trigger the comparison. Then we first compare the administrative distance. So when we compare now, smaller is better. So, 1 is 1. 1 is 2. Obviously the first one is better. If the first one is better now, the second item will not be added. Let's look at the routing table now. Its next hop is only 10.1.1.2. It will not be added to the table. So for two routes, now its administrative distance is not the same. The principle of adding tables. We'll select an optimal table addition. So there will be no other route. But that's just saying. Now only one route appears in the routing table. Then according to what we just said, this situation is drawn in this picture. How can this line complete a switch? That is our scene. The reason why one line is the main line. One line as backup line. It is hoped that the daily traffic will take the main route. If the main line fails, take the backup line. So how can we let the main line fail? Very simple. I just need to enter the interface. Just shut down the interface for it. Let's say I'm on the device on the left. Our interface to the main line. Then give it shutdown. Then once I shut down now, we can observe the phenomenon. Excuse me. Is the route still there? Let's check. The route just now is gone. Now the next hop that appears in the routing table becomes 20.1.1.2. That is, becomes the address of this interface. Now the traffic goes the following route. Why once this interface is gone, the corresponding route disappears? For routing, if the physical state of a port is up, then the corresponding direct route exists. Remember the direct route we talked about earlier? That is, this interface is configured with an IP and no shutdown. The peer also has an interface. It means that the physical state and the protocol state are both up now. A direct route will be generated. This is what we said before. The physical state of the port is up. Then the direct route exists now. Then if the physical state is down, actually, This interface is not working. Then the direct route disappears. So for the current environment, because the ports are down, there is no such direct route. Its next hop is of course unreachable. So this route is correspondingly gone. Because now the next hop is the direct connection. Then this interface is actually down. If there is such a route in the routing table. Future visits. I can't forward it. Because the interface is gone. It doesn't make sense. Let's test it now. For example, I ping 8.8.8.8. Still works. Because the route must go the following route. Then if I restore this interface now, will it retable? Okay. It will be relisted. Because if the route comes back, to retrigger the comparison again, we can verify. For example, I entered the 00 interface. I turn on this interface, no shutdown. I hope it pops up some log messages later. Okay. Finished playing. Let's check now. IP route. Okay. Now in the routing table, the next hop becomes 10.1.1.2 again. That is, it's on the line again. Route restored. So we will now find if when this interface is enabled, the next hop in the routing table becomes the main line. If this link fails, then the next hop in the routing table becomes a backup line. So, given that we have defined the administrative distance, in fact, as long as the main line does not fail, it is forwarded normally on a daily basis. If it fails, go the following line. If it recovers, go the above route again. So this route about 8.8.8.8 in the routing table is always changing. That is, according to the current real forwarding situation of the main line. If it creates problems, it just sinks. If it's okay, it resurfaces. So we call such a route a floating route. Usually, it's actually called route backup. It is a backup technology. I now have an extended question. For example, now this interface is all fine. But if you get into this device, I put it on the interface, and if it is down, do you think I can ping now? We are now on R2. Enter the interface of R2. 00 interface. Shut down. I now down this interface. If I look up the table on R1, how much is the next hop? I repeat. If R1 goes to 8.8.8.8, the next hop is this interface. So we just verified. If I put the router on the left, this interface is down. The routing will switch to the following line. If this interface recovers, just go the above route again. That is, regardless of whether the interface is down or not, can be pinged. If it is down, switch to the backup line. My problem now is, this end of the line is fine. But if the interface on the opposite end is down, the flow cannot be switched now. Because I'm already shut down now. Okay. Let's verify. Actually, let's see if the routing of R7 is correct. I'll check it now. Show IP route. You will find, obviously, the device on the right. Enter the 00 interface. Already shut down. And now this state. It is indeed down. Then why is the next hop here still 10.1.1.2? This interface has been down. But for the device on the left, it does not know that the interface is down. Its current next hop in the routing table, still this interface. Then the future data will go to 8.8.8.8. It will still forward according to this interface. But now there is a problem with the physical state of this interface. Then data traffic is sent. It is impossible to receive. So you will find, if there is a root, it will receive the data. If no root, it directly lost the data going to 8.8.8.8. There is now a local root. It checks the routing table and forwards to the next hop. There is now a problem due to the next hop. Then actually, data here. It is impossible to receive. So, there was a problem when data was transmitted on this link. This phenomenon is called routing black hole. When a data arrives on a device now, this device obviously has a route to the destination, and also perform data forwarding on the data. But the data didn't reach the destination. This phenomenon is called a routing black hole. When you learn BGP in the NP phase in the future, we'll touch it. This is a very typical phenomenon. What we are talking about today is also called routing black hole. Do you know how to solve it? Certainly. NA stage will not talk about this thing. I just want to mention, we will learn a little tool in the future. It is a link detection mechanism of Cisco, called SLA. This will be learned in the NP phase. Now the problem is that this interface is down. But this device is not aware, since it has no way to perceive. So it has no way to know that the interface is down now. That's why I added a switch in the middle. Direct connection of devices is also called direct connection. Actually, it has two cases. A direct connection in the physical state. That is, there are no other devices in between. The inner end of the interface of one device is the interface of another device. This is called direct connection in physical state. For the R7 and R8 we talked about today, a switch intervenes between them. This kind of direct connection is called logical direct connection. The switch does not affect the real data forwarding, but it affects them not being directly connected anymore. This interface is down due to the intervention of a switch in the middle. This interface cannot perceive that it is down. If they are directly connected, it's down. This interface is also down, because this interface can directly sense that the peer link is down. This link is no longer available. But because a device intervenes, it is imperceptible. So we will learn a method in the future. Let R7 perceive that the 00 interface of R8 is down. Then switch the route to the following line. Rely on the technology of SLA. This is a Cisco link detection mechanism. The device on the left keeps sending messages to the device on the right to detect the carrier A nature of this interface. If it works, we'll reply to the device on the left. Then finally bind the SLA to the above route. That is, bind the SLA to this route. This is the route of the main line we are using now. In the future, through a detection mechanism such as SLA, to detect the other party's interface. If the peer interface is down, then the SLA is down. Since it is bound to this route, then this route will be down. Down means to come out of the routing table. It no longer does normal data forwarding. Then the following line will reappear in the routing table. That is, I pass a detection mechanism. Check the status of the other party's interface. If the status of the peer interface is down, SLA will be down. Due to the SLA and this static binding, then this static route will also be down. Then if this static route is down, let's go back to our original idea. If the above line is down, the following line will float to the routing table. It is also a floating static route. Let's not talk about this configuration now. Only in the NP stage. But you need to know this. Okay. Let's move on. Default route. Actually, I told you before. For current equipment, RA wants to reach the network segment behind RB. You will find it has entered 3 network segments here. Then in theory, if I configure it here, how should I configure it? IP route 192.168.1.0, 3255 and 10. The next hop is 12.1.1.2. This is the first. If the data wants to go to 2.0, IP route 192.168.2.0, 24-bit mask. The next hop is also 12.1.1.2. The third is the same. You will find, as long as this network segment is behind the RB, which network segment does the data actually go to? The next hop is the left interface of RB. So traffic will be sent to RB anyway. For this case, we can enter a default route. It is represented by 4 zeros. The next hop points directly to 12.1.1.2. That is, as long as the data goes to any place in the future, can send traffic to RB. Of course, the premise is that there is no precise route in the routing table. For example, a route is now entered in the routing table, 192.168.1.0, 24-bit mask. Then if there is a route to the 1.0 network segment, it will match the following. Does not match the above. I should have told you about this in the last class. Let's take a look at its configuration. IP route. For example, I now simply configure a route for it. 0.0.0.0. The mask is also 0.0.0.0. Suppose the next hop is 10.1.1.2. Okay. Let's check. Just check the status. There is now a default route in the routing table. The reason why I entered this command for you. I want everyone to see this phenomenon. That is, the form of the default route. In the routing table, it will be denoted by an asterisk S. When none of the routes can match in the future, match the default route. So where is this thing most used? I give a simple example. For example, on PC. PC has a default route. We can check it out. Route print. There is now an IPv4 routing table. The host also has a routing table. Now the mask is 0.0.0.0. The reason is not 4255. Because there is a longest mask matching principle. 0.0.0.0 represents all routes in the entire network. Then the next 4 zeros represent any mask. There is no restriction on the network segment. No restrictions on masks. Because it is the combination of IP address and mask. To define the network segment. Now it can be any network segment. For address and mask are not matched. Including when we go to match in the future. The mask is the longest to match. If now the mask is 4255. It's 32-bit. Then send any piece of data. It must match the route. Default route forwarding. That's wrong. Because 4255 are 32-bit masks. For equipment, it's also 4 zeros. There is a gateway here. The data is forwarded. Now your computer can access the internet. Thanks to such a default route. Other than PC. It will also be used on the company's public network export. Let's say this is the company. This is the operator. Then I want to access all the data on the public network. Such as Google, YouTube, Facebook. They are all public network services. Available through the operator. Forward the data. In company export here. We'll enter a default route. Point to the device that the operator connects with us. That is, in the future, no matter where your data is sent, The traffic is handed over to the operator. Let it help forward this default route. It is a default route that every company export will have. As long as the company is now using the internet business, there will be a default route. The next hop is pointing to the operator. The export is configured like this. For export, it's just a device. Its configuration is IP route 0.0.0.0, 0.0.0.0, Internet address of next hop carrier and company. Generally speaking, this internet address configuration is the company side and the operator side. When handling carrier business, it will provide the internet address. If the future uses dial-up internet, such as the form of PPPoE, then it is another form. Then the exported IP is not fixed. If the enterprise handles fixed bandwidth, if there is a public network IP here, there is also a public IP here. Now the most used is a 30-bit mask. That is, only 2 addresses are available under the 30-bit mask. One end for the company. The operator at one end uses just use the next hop to point to the operator. As for how to get back the operator data, we can't talk at this stage. The future IE stage will talk about. A default route points to the past. Don't worry about how it came back, because this is the configuration of the operator. For business, when configuring, it is to export a default route pointing to the internet address. This address is when doing business. The operator will provide. Okay. Let's summarize the problem of static routing next. When we were configuring in the last class, everyone will find a problem. The overall configuration of static routing is very complicated. It's not that its mechanism is so complicated, but the input on each device is complex.